Now, the new idea was quantum information. The basic notion of quantum information is the qubit, the quantum bit, and I show you some visualization here which we tried, and I should warn you, one cannot really show quanta. This is not possible. But it's just a matter to help us with the imagination. Here is a representation of a classical bit. Today, everybody knows, because we play with computer, that the bit is 0 or 1. Here is a classical bit, it's the switch, which can be 0 or 1, depending on whether it is on or off. A quantum bit would be in a superposition of 0 and 1. It is not that it is a bad switch, but it is really in both positions at the same time. So it would not be 0 or 1, it would be 0 and 1. And now you can imagine that this fact, and it actually can have different amounts of 0 and 1. So you can imagine that this fact allows you to store much more information in a bit, in a quantum bit than in a classical bit. And it allows you new manipulations which are not possible with classical information. And this is the reason why people believe that quantum communication using individual quanta to communicate, or quantum computation using quanta as the core of a computer, will result in a new technology which basically beats everything which we have now. Another notion I want to introduce now, besides randomness, is the notion of entanglement. This is a famous paper by Einstein, Podolsky, and Rosen, published in 1935 in Physical Review, where they realized that if you have two particles which had some interaction in the past and they are separate, you can have the situation that measurement on one instantly, no matter over which distance, changes the state of the other one. Einstein did not like it, and he called it spooky action at a distance, and he was hoping for a new physics where this spooky action would not exist. One of the co-authors tipped off New York Times, and they wrote this kind of article, Einstein attacks quantum theory, scientist and two colleagues, the other two colleagues were also scientists, but never mind. But I guess if you work with Einstein, you are not a scientist. He's so much above, doesn't matter. Find it correct, even though it is find it not complete, even though it is correct. And so this shows you how bad some journalists write stuff, even in the New York Times. But this doesn't matter. The important point is that Erwin Schrödinger, I showed him to you already, realized immediately how fundamental this notion of entanglement is. And he says entanglement for him is the most fundamental notion in quantum physics, the one which forces us to abandon our cherished views how the world works. I would like to show you this in terms of a game with a pair of dice. If I have a die here and I throw it, and it shows a 4, how likely would it be that if I throw it here, I also get a 4? Luckily, no, it's a 1. It's not the same number. But imagine now that I had a pair of dice where it's always the same number. Now it's a 4. Next time I throw it, oh, it's again a 4. That's amazing. Next time I throw it, I get a 1. And if I would throw this one at the same time, I would also have gotten 1. This is the notion of entanglement. If these were quantum dice, which you cannot buy yet, but I promise in 100 years you can buy them. If these were quantum dice, they would show the same results every time you throw them, no matter how far they are away. The point now being is that each of these results is completely random, in the way I mentioned before. So how can it be that two completely random events give you the same result? And this is what brought Einstein to make the statement. This is the most important feature of quantum mechanics. You could have two different kind of explanations to help a common sense mind to interpret the things. Interpretation A would be to say, oh, maybe there's a hidden mechanism in both of them, where it's pre-programmed what they will be, and now it's pre-programmed to give 1, next time it's pre-programmed to give 9, or what, to give 6, or whatever. So just some hidden property. And the second possibility of explanation would be is maybe there's some communication between both. A very sophisticated communication, again an internal mechanism, and this one decides to give the 6, and it tells the other one it will also give the 6. And there's a lot of experiments now have been going on in the last 30, 40 years to rule out these possibilities. And we now know that none of these possibilities is possible. We have to live with the fact that these are 2 random events which are each completely random in the sense, as we mentioned before, there is no hidden explanation why it happens the way it happens, but they're always the same. So here is just to show you the importance of the paper. These are the scientific citations in scientific literature of this Einstein-Podolsky-Rosen paper over the year. It was published in 1935, and you know the number of citations is a measure how important the paper is. It was quoted only 5 times in the first 3 years, and then it was ignored. So it was a bad paper in that sense. And then it picks off in the 1970s. We have a lot of interest because somebody suddenly found out that you actually can test these assumptions, which I mentioned before, that there might be a hidden communication over there. We really can test them in experiment. This is Bell's theorem. And then to the big surprise of everybody in the field, we happen to be on such experiments early by chance. To the big surprise of everybody in the field, it turned out that this notion of entanglement, as Schrödinger calls it, became a basic procedure for quantum computation and things like that. Nobody expected that, and now you see that the paper is quoted about nearly 250 times a year, which I like to say does not mean that it is read more often than in the old days. But that's a separate story. Bell's theorem, I mentioned, Bell's theorem was the theorem which allows us now to check these kind of ideas, which I mentioned for the dice, whether there's some hidden mechanism. The experiments work with a source, sorry, this is a strange language here, with a source which puts out 2 photons, 2 particles of light, which can be entangled such when you measure their polarization with 2-channel polarizers here. It turns out that both are either always horizontally polarized or they're always vertically polarized. So 2 possibilities, not 6 like with the dice here. And what Bell showed is when you do measurements, when these polarizers are not oriented parallel but at angles, then the correlations between both sides in quantum mechanics are stronger than any such classical explanation. This is called a conflict of quantum mechanics with local realism, that what happens here is local, it's independent of what happens on the other side, and it's some property hidden in the system which we don't know, but it's a real property. This led to many, many experiments which all confirm quantum mechanics and realism is in troubles. There's a nice article I can recommend to everybody of you, written by John Bell. It is called Bertelsmann's Socks and the Nature of Reality. It's a very strange article for a strange title for a scientific article. What he argues there is the following. There's a physicist, he really exists. He's a colleague of mine in Vienna by chance. John Bell was at CERN in Geneva. And he always wears different socks. As a matter of principle, he never has socks with the same color. So when you see, Bell says, when you see Bertelsmann coming around the corner and you see a pink sock, you know definitely that the other sock is not pink. And the explanation is very simple. The explanation simply is because he put on different socks in the morning. So the color of socks in that case is an element of reality. It is real. And then Bell goes through a very beautiful argument without formalism, without philosophy, where he argues and convinces you, I promise, he convinces you that why in quantum mechanics we say if these were quantum socks, you would get the same result. One is pink, the other one is not pink, but the assumption that the socks had their colors before you looked at them is wrong. And that's the basic point. That's the basic point, that you can have situations where the observation makes, I would not say creates the result. This is already interpretation. where due to the observation, a system has definite properties, but we know that before it could not have this, because this leads to a contradiction. That doesn't work. Okay? So this is the notion of the quest for realities, I would call it. Here are the experiments which Professor Ellis mentioned in his introduction. This is the long distance record for such quantum experiments. We create pairs of photons on the island of La Palma. This is at the Canary Islands, which are about a few hundred kilometers west of the West African coast in the Atlantic Ocean. And we send, of these photons, we keep one locally in a glass fiber, and we send the other one over to the island of Tenerife, where it is caught by telescope, and its polarization is measured. Here's the telescope which we use. This is actually not an ordinary telescope. It's a special telescope. Why it cannot be an ordinary telescope? As everybody of you who ever talk to astronomers knows that their telescopes usually go down to maybe 20 degrees or something. Because if you go down all the way down to the horizon, you don't see much anymore. So it doesn't make sense to build such telescope. This telescope was built by the European Space Agency to develop optical communication with satellites. And if you want to follow a satellite, you have to be able to go all the way down to the horizon. You don't want to lose the signal. So this is a telescope and they built it for optical communication with standard laser light. We are using this telescope to look over to La Palma to catch our individual particles of light, our individual photons. Here a picture how the setting looks like there, if you are there on the islands. This is the source on La Palma. Here's in here we have NOT means Nordic Optical Telescope. We keep one photon locally in a glass fiber, send it around and measure it sometime later after it has been measured, and the other photon is sent over to Tenerife, where it is also measured. Okay? Here's the radio link for a special experiment, but that is not important. You can imagine here, this is 144 kilometers. And believe me, when you stand up there, it's really far away. And it always amazes me that one can catch individual particles of light after such a distance. That's a picture I've seen from the OGS, Optical Ground Station on Tenerife. Over there is La Palma. This is El Teide, the highest mountain of Spain, which has an altitude of 3,800 meters. Here's the reception station for our individual photons. As I mentioned, we have tested this entanglement over this distance, and we have closed some loopholes in the interpretation of the experiment of the kind I mentioned before, because you can imagine over this distance, when you measure the two photons, you really can make sure that no signal about this measurement can travel to the other one before this measurement is made. So this is really completely independent. And the other features of the setup, what we do is we have on this side we have on both sides we have a quantum random number generator, which decides randomly which polarization should be measured on this photon, same on the other side, and sent very fast to the detection station. The point here is that we want to make sure that the choice, what is being measured, can also not be influenced by the source or by the other side, or that there cannot be any interaction between the possibilities. Now, I want to discuss a little bit the philosophical possibilities which we are left here now. One is that we assume that locality is not true. So in any way, even as Einstein says that nothing can travel faster than the speed of light, maybe the two dice know of each other instantly. The other possibility, which is always a logical possibility, the other possibility is that the world is completely determined. There is no freedom. What is important in the argument of Bell's theorem is that the experimentalist is free to decide what she wants to measure, what feature she wants to measure on the particle. If this freedom does not exist, if everything is completely determined, then we have no problem. But if that is the case, then I ask myself, what am I doing when I do physics? When I do physics, I believe that I can ask free questions to nature to find out something new. If this question is also determined by nature, nature could fool us around, right? She could tell us to ask this question or that question, which is irrelevant or whatever. It would be the end of science, I would argue. Another possibility is that you have actions back into the past, in the sense when you have my two particles, which were created by the source and which are measured, that actually back into the past, the measurement influences the source some while ago and tells us what the source has to admit. This is also very unusual, that you have influence back into the past. Another possibility is that Aristotelian logic breaks down, which is if A is equal to B, B equals to C, then A is equal to C, this kind of simple reasoning. And the possibility which I like most is that our picture of reality is not tenable, at least not the picture which we have in everyday life. It is not fair to assume that what we observe when we do a measurement has existed in all cases before I do the observation. Okay? Now, the reason why I believe that, the research program in my group has been to try to focus in onto this question more and more with new experimental ideas. One of the experimental ideas is the 5 cups, which I want to play with you now. Here are 5 cups. With 5 cups, and I have 5 dice. Okay? You have 5 cups, 5 dice. As you can see, the dice have different color. They are purple and they are blue. I hope you can see it over there. And the task, a magician is given the task to distribute these. The numbers don't matter now anymore, so don't worry if you cannot see them. A magician is given the task to distribute these dice such that whenever he opens 2 neighboring cups, he gets 2 different colors. Okay? Now, let's play the game. I open these 2 neighboring cups, I get 2 different colors. Easy, I've won. I open these 2 colors, I get different colors, I've won again. I open these, I've won again. All right? So it's very easy, right? I open these, I still have won. And now I open these and I have the same colors. So I could only succeed in 4 out of 5 cases. And there's no better way to do that if these are 5. So the classical optimum, we say, is 4 out of 5 cases. Now, quantum mechanics, and this is the next part of my story, quantum mechanics tells us that there are situations, if these were, again, quantum dice, in a very special situation, that sometimes you actually can have in 5 out of 5 cases the same color. So when you cover it, and you look at any of the 2, you look at these, you get the same color, they're different, and you would get different here too. It actually turns out that on the average, in 4.5 cases, you get the different, which means that in half of the cases, you get different in all 5, and in half in all 4. Now, I tell you now how we do it in experiment a little bit for the physicists. I know this is now a little bit the harder part, but what is the message? The message is, for the magician, this doesn't work because the color has, these buggers have to carry the color before you look at them. They have to be in there. In quantum mechanics, this is not necessary. You can prepare the system such that the instruction is, your color have to be different, but not telling the particles what color they have to have. Okay? Now, how do we do this? This is now for the physicists among you. How do we do this in experiment? For the non-physicists, it'll be very short. Don't worry. But you can take a little nap now for 2 minutes. So this, what you see here is a sphere, and what this is different directions in space. And there are 5 different directions in space. These directions are pairwise orthogonal. Like A1 is orthogonal to A2, this is orthogonal to A3, to A4, to A5, and to A1, okay? And they form a pentagram. You can see a little pentagram here. They form a pentagram. And it turns out that if these are the directions along which you measure a spin-1 system, which is an eigenstate to the direction to the center of the pentagram, then the squares of the spin components pairwise commute. So you can measure them at the same time. And the pairs of the spin components just play the same role as the color here. Instead of purple and blue, I have 0 and 1. They commute. And it turns out that I can have a situation where this is a situation invented by Kliashko, colleagues in working in Turkey. You can have a situation where an inequality which you derive from here, assuming that now, more strictly speaking, that the individual measurement results are given by probability distributions. A definite result includes a probability distribution, limit the correlations, and quantum mechanics violates them. How do we do the experiment? Now I can tell again the non-physicists to wake up. What we do is we realize the system such that we have one photon, one particle of light. Remember, we had superposition of the two slits. Now we prepare the photon to be in a superposition of 3 modes of propagation. This could be 3 glass fibers or just 3 different beams propagating and so on. And then what we can do is we play with these two beams. For example, we can mix them with mirrors, or we can interchange them, or whatever you want. And the question simply is the probability to find whether I find the photon here in this beam, which doesn't know anything about so the photon could be here or here or here. Is the probability whether I find a given photon, which was started long time ago, here, does it depend on whether I manipulate these beams up there or not? The answer must be no. How should it know? This would be silly. Quantum mechanics says no. It depends on whether I find the photon here, depends on whether I manipulate these things here, yes or not. So in terms of our dice, it means that for example, the color of this bugger here, depends on whether I measure it together with this one or together with this one. Okay? So this tells us that systems don't have the properties before we look at them. You can see this as a realization of this beautiful waterfall of Escher. This is a famous picture. You see water flowing down here and flowing down here and flowing down here and flowing down here and falling down. The waterfall is always down, down, down. Each piece of the picture makes sense. In the quantum picture, each piece makes sense, but the all together doesn't make sense. This was actually pointed out by Roger Penrose a long time ago. Now, this quantum idea comes from Simon Kochen, who is now a retired professor of mathematics in Zurich, and Kochen is a retired professor of mathematics in Princeton, and Erich Specker, who is a retired professor of mathematics in Zurich. And this is long ago, and it took a while to develop this kind of experiments. Actually, the idea of Erich Specker was the question whether infuturabilia exist, as he calls them. And now we are again in a philosophical debate. He asked the following question. He's actually a preacher in some church in Zurich. And he asked the following question. This is not serious. Suppose we all show up on the day of judgment in front of God. And God has to judge whether we have done well or not. Then it would be very handy for God to know not only what we did, but also what would have happened if we had made other decisions. And the question is, can God always know that? And Specker's answer is no, he cannot, because in quantum mechanics, you cannot You cannot assign properties to systems. You cannot talk about the truth value of situations in the whole measurement context. And the whole measurement context exists only once. It's only the context of the experiment which you actually do. So that might help some people to get off the hook on the day of judgment. Now, again, back to possible applications. I mentioned to you that the big surprise for many in the field was that this kind of thing led to applications which nobody expected. And we have the large field of quantum information emerging now. The furthest developed idea is quantum cryptography, where Alice and Bob, they want to share some secret, and they want to communicate secretly. They have a classical channel, telephone, internet, you name it. And in addition, in quantum cryptography, they have a quantum channel which allows them to establish a secret key. And the idea now is the following, that an eavesdropper who can, want to see it again? There you go. An eavesdropper who could have access to all these channels, you don't know to what an eavesdropper has access, would be detected because you cannot observe a quantum system without changing its state. So that would immediately mean that people stop their communication. Here's an experimental realization of this kind. What we did in this experiment was to send a picture of the Venus of Willendorf. This is a very famous prehistoric little effigy which was found near Vienna. It's a very famous figure, actually. And actually, it was the first time that a naked lady was pictured in Physical Review Letters, which is the top physics journal in the world. Okay, but this was not our motivation. Our motivation was that my young colleagues came and said, now we want to show this in a nice way, and we want to encode some picture. And they came with a picture of a bomber, something like that, and tell them, you have to find something which is peaceful and which is Austrian. Okay? So what happens is, this is the quantum key. It is established by measuring many pairs of entangled photons. Many pairs of entangled photons, which always give you the same result, each pair, but different outcomes, 0, 1, 0, 1, whatever. It's a big random sequence. And this is the optical representation of about 60,000 bits of random sequence here and here. And because of the entanglement, these two sequences are identical. So what we now do is we mix point by point, we mix this picture with this one, and we get out a random encrypted picture. And because this is completely random, irreducibly random, there's no hidden way how a computer could attack it. This is a cue against eavesdropping. But the recipient can decode it because he knows what the key is. I'll give you another example of quantum computation, just to whet your appetite. There is a scheme. Quantum computation is a huge activity worldwide in many laboratories because quantum computation promises computers which are not only much faster, but which are able to solve problems which existing computers cannot solve. And my personal conviction is that someday we will have a quantum information technology. There is no fundamental reason why it should not work, but there's huge technical challenge. To me, the nicest concept of quantum computation is one-way quantum computation. I try to image this a little bit. These are many qubits, many quantum bits. They could be photons, or they could be atoms in some quantum state sitting in some lattice or whatever, you name it. Okay? And they are all entangled with each other. And then this is how the computer starts. And it's always the same state with which the computer starts. And then the calculation is performed in such a way that the program is nothing else than a measurement sequence. Let me explain. It says, first measure this qubit. What happens is some random result. And what the measurement does, it projects or forces the remaining qubit into a new well-defined state. Then the procedure says, then measure this one, and then measure this one, and so on. And you can form the sequence such that after n steps, the remaining qubits contain the answer to the question which you want to solve. So you tweak the state, you force the system to evolve into the answer of the question which you have. Now, to me, this is quite fascinating. It's the realization of what is called the infinite library, was invented by the scholastic philosopher Raimundus Lullus and put into a nice novel by Jorge Luis Borges, the famous Argentinian writer. Or he also calls it, in the English translation, I think it's called the Library of Babel. It's a library which contains all books which have ever been written and which will ever be written. How can such a thing exist? Very simple. You simply print books with all possible combinations of letters. Now, clearly, this library is completely useless. It turns out, actually, formally speaking, that to find the right book which you want is of the same complexity as to writing it right away. It doesn't matter. It doesn't help. This quantum state is the quantum realization of this infinite library. Because it can be shown that there are quantum states which are universal, which means that they are complex enough such that they contain the answer to any possible question which you can ask. And this, to me, is absolutely fascinating. It tells us something about computation which at least I don't understand yet. Now, I want to come slowly to the end. One of the things which we are playing with is quantum teleportation. You know, teleportation is known from science fiction. Everybody of you knows this word, beam me up, Scotty. I actually saw some of this. I'm not a TV watcher, but I saw some of this with my boys because they like to watch these Star Trek movies. And let me just now seriously analyze what happens. You have an object. You scan the information carried by the object. You transfer the information to the new station where you want them to arrive, and you reassemble the original using this information. Now, the interesting point is that quantum mechanics tells us, because of what is called Heisenberg's uncertainty relation, the first step is not possible. You cannot extract all the information which characterizes the system in quantum mechanics, because the quantum measurement actually changes the state of the system. It's not possible. So it's not possible to do this. And the people who did these Star Trek movies knew that. And for the Star Trek aficionados among you, you know that they invented the Heisenberg compensator to compensate for that. And one of these guys was once asked in a press conference, how does the Heisenberg compensator work? And the answer was, very well, thank you. Now, the interesting point is, like always, quantum mechanics comes to the rescue. Using entanglement, we are actually able to teleport the quantum state, here's an unknown quantum state, over to some recipient. We are actually able to teleport this, even as we are not sending the state itself directly. And this is done using entanglement. We have an entangled source here, which produces two photons, entanglement, and entangle the one you want to teleport with one of the two entangled ones. There's a lot of entanglement here. But the basic point, I don't want to go into details here, is that you can teleport the quantum state to a receiver station over any distance. Now, this is not a future means of travel, but it is a future means of communication between quantum computers. The future seriously is in space. We are working to put some of these quantum sources on satellites to have worldwide quantum communication, like quantum cryptography and so on, between any two stations on Earth. I want to close with some philosophical remarks again. The old question is, how real is reality? You know, many books have been written about this question. Supposedly, Albert Einstein, remember? Albert Einstein, Niels Bohr. Albert Einstein demanded physics to describe reality as it is out there, completely. And Bohr said, no, Einstein can only be about what we can say about reality. supposedly Einstein asked one. I was not able to verify whether this really happened or not, but it is everywhere. So it might be. It's a story too good not to be true. The question is: the moon there when nobody looks? Do you really believe that the moon is there when nobody looks? So, to which supposedly Bohr said, "Prove to me the contrary." How can you prove it? You can only prove it by looking at, including measurement and so on. Okay? So, but there's one interesting point, and I would now like to seriously suggest, in physics we have learned that we should not make distinctions which are not warranted. Very often distinctions which we made are based on our prejudices and our expectations. For example, and when we don't make this distinction, we make a big progress. For example, Newton found out that the same laws which describe falling an apple on Earth, or falling a die on Earth, actually describe the motion of the celestial bodies. So he unified the laws on Earth with the laws in heaven, which was a big achievement. There are many unifications like that in the history of physics. Now, to me, the distinction between reality of information is a similar artificial distinction. This is now my personal opinion, okay? Because we cannot operationally separate the two. Whenever we talk about reality, even think about reality, we really handle information. The two are not separable. So maybe now this is speculative here, maybe the two are the same, or maybe even information is constitutive to the universe. And this reminds me of the beginning of the Bible of St. John, which starts with, "In the beginning was the Word." And I know that this is not the only tradition in the world which says that, something like that. So in the end, I just want to underline, this is, a lot of this research is going on actually a lot of quantum computation research is going on in classified laboratories, and this proves that the Americans are far ahead of us. This is a parking lot near Washington, D.C., and evidently they already have quantum cars. Thank you very much for your attention.